We're ready for section 6.3, inverse trigonometric functions. Now, before we talk about inverse functions, let's recall what our sine function looks like. I'm going to graph it here on the left. I'm going to graph it kind of quickly. Remember, our period goes all the way out to 2 pi. We cut it in half here at pi. We're here at pi over 2. This guy here is 3 pi over 2. It goes up to 1, down to negative 1. And we have our 5 points. And that's one period of the sine function. Now, when we start talking about inverses, recall that the function has to be 1-to-1. In other words, not only does it have to pass the vertical line test, which this does, but it also has to pass a horizontal line test, which this does not. It repeats a lot of the y values. So in order for us to use inverse functions for trig, we have to restrict the domain. Now, if you notice on that first hump there between 0 and pi, we double up on y's already. And whenever you restrict a domain, you really want to stay as close to the origin as possible. So what the mathematical community forever and ever have decided is that they're going to restrict the domain from negative pi over 2, where it's negative 1, up to pi over 2. So they are going to use just this portion when looking at the sine. So notice below, if we restrict the domain of the function to negative pi over 2 to pi over 2, then our range is strictly negative 1-to-1, and there are no repeated y values. So that means the domain for the inverse function is the same as the range of the regular function. The domain is negative 1-to-1, and the range of the inverse is negative pi over 2 to pi over 2. So if we were to graph the inverse function, remember the values would be backwards. Our input or x values would go from negative 1-to-1, and it would go from negative pi over 2 for the y value up to pi over 2, and it would look something like this. So here is our reminder down here to recall. If f of a equals b, then whenever we take the inverse function, the f inverse of b equals a. Those points switch. So the same thing is true for the sine function. If you're taking sine of an angle theta and it equals a y value, then when you do the sine inverse, that argument is now the y value, and it should give us the angle back. Now they use two different forms. You may see it as inverse sine written like this, sine with a -1, or you may see it as arc sine. They're the same thing, don't get confused, so they're going to switch them out just so you get used to both of them. But remember, this is only true between negative pi over 2 and pi over 2. Let's take a look at these two examples. If sine of pi over 4 equals rad 2 over 2, then the sine inverse, notice now they're giving us that ratio, that y value, rad 2 over 2, will give us pi over 4. And pi over 4 is between our negative pi over 2 to pi over 2. If it helps you more to think of it in terms of the unit circle, negative pi over 2 to pi over 2, first and fourth quadrant. So let's take a look for the arc sine of negative rad 3 over 2. Remember, the negative rad 3 over 2 is the larger y value. So in the first quadrant, we would be looking at 60 degrees or pi over 3. But remember, it's negative rad 3 over 2 for the y, so it would be down here. So that would be a negative pi over 3, and that would be our answer. So now taking a look at the cosine function, let's focus on what the original equation looks like first. I'll draw it quickly. So notice this is just one period of our cosine function, but again, it does not pass that horizontal line test. It needs to be 1 to 1. So this one, though, hits all of our y values from -1 to 1 between 0 and pi. So our domain for our restricted function, in order for us to find an inverse, is going to be from 0 to pi, and our range again from -1 to 1. That also means that the inverse for the cosine, the domain will be from -1 to 1, and the range from 0 to pi. So that means our x values are going to go from -1 to 1, and our y values from 0 to pi. So the same idea, remember, if f of a equals b, then for the inverse, f inverse of b equals a. Same thing's true for the cosine. Cosine of an angle equals x, that ratio, then the cosine inverse will have the x value as its argument, the input, and the angle would be the result or output. And again, they use both a cosine inverse notation or arc cosine. And again, it's restricted between 0 and pi. Similarly to the sine function, the tangent function is restricted also between -pi/2 and pi/2. If you remember how we graphed that guy. So for a tangent, we only look at that one period between -pi/2 and pi/2, but notice it uses parentheses, not brackets, because we can't have values at -pi/2 and pi/2. But the range goes from -infinity to infinity. So when we draw the inverse, that means that our domain for our x is from -infinity to infinity, but our range only goes from -pi/2 to pi/2. So once again, f of a equals b, then f inverse of b equals a. So if the tangent of an angle equals the ratio y/x, then when we look at the inverse tangent, the input's going to be y/x, our output's going to be our angle. And again, they can use the inverse notation or arctan, and it's between -pi/2 and pi/2. Now let's get into the fun stuff. Let's find the value of each real number of y, if it exists, and we're going to check our calculator. We can check our answers in our calculator if we wish. So y equals sine inverse of -1/2. So this is asking sine of what angle equals a -1/2. For some of us, it's easier to work in the unit circle. For some of us, it's easier to work in the graphs that we just did. Both of them work fine. If you're doing the unit circle, since it's a -1/2, you know it's going to be down here in the fourth quadrant. And so that would be -pi/6. And again, even though there's also a -1/2 in quadrant 3, since the original problem is an inverse function, we can only look in quadrant 1 and quadrant 4. So in part B, we're looking at the arc sine of rad 2. So that is asking us the sine of what angle would equal square root of 2. But now we have a problem, right? What is the square root of 2? It is approximately 1.414, which is greater than 1. Okay, so this is not in our domain. So it does not exist. The arc cosine of 0, again for cosine, we're going to go from -1 to 1 on the unit circle. And so that x value is 0 here up at pi/2. And then the tangent inverse of -1, that is asking us tangent of what angle gives us a ratio of -1. And remember, there's only one angle where your y and your x value are the same, and that's the multiples of the 45 degrees. So we have theta of a negative pi over 4. Now, we can use our calculator to check these. All right, so on our calculator, notice we have the inverses here above the sine, cosine, and tangent. Remember, these do not mean reciprocal. Now they're giving us the inverse function. So on our first one up here in A, we were doing sine inverse of -1/2. So we can do second function sine to get the sine inverse. And we can plug in the -1/2. And notice we get this -0.523598. And we may be going, I'm not quite sure which one that is. They will always give you the decimal format. So we can check. We can put in second function pi divided by 3. We go, nope, that's not it. Let's do second function pi divided by 6. Hey, that's it, but it's the negative version. So we can double check, yep, our -pi/6 was the correct value. So even if you go blank, go, shoot, I don't remember which one it was, you can always plug it in and it will give you the decimal form and then just check to see which of those is the decimal form. Hint, hint, wink, wink, nudge, nudge. But on the second one, it said the arc sine of rad2. So you have to remember that arc sine is the same thing as the inverse function. So we can do second function sine and then plug in the square root of 2. But notice what happens. Oh, that's interesting. Hang on. Square root of 2. We hit enter. Note it says there's an error in the domain. It will tell us, hey, we messed up. Okay, there is an error in the domain. So we can go back and just say, hey, it was too big. All right. Now for this third one, y equals arc cosine of 0. Again, we do second function cosine to get the inverse. Plug in 0, and it gives us 1.57. And again, we're not quite sure if we were correct, but we'll try it. We'll do pi divided by 2, see if we get the same number, and we do, so we were correct. And then last but not least, tangent inverse of -1. We get a -0.785, so let's see if we were correct. And this time we can even put in the negative. Second function pi divided by 4. Hey, look, and we got the same result. So it's just a nice way to check it. And again, be sure we're putting in radians for our answers. So be sure that your calculator is in radians. Now, composition of functions can be kind of fun because you really have to focus on, okay, so which one is the input, which one's the output, and where are my restrictions? So notice here, we have a composition of sine inverse of x, and they do equal x. Okay, so the original function and its inverse, they undo each other. And we've talked about that before with composition functions. Inverses, when you take their compositions, they always equals x back and forth. But notice how the restrictions may or may not change. So sine of sine inverse, that input has to be defined. So that means our x value has to be between -1 and 1. Same thing for cosine, between -1 and 1. The output will have the restriction as well. And then tangent inverse for x between -infinity to infinity. When it's the other way around, notice the input now is the actual angle. So that's why we have from -pi/2 to pi/2, cosine 0 to pi, and tangent -pi/2 to pi/2. So let's take a look with some examples here. Example 2, we want to evaluate the expression below without using a calculator. Sine pi/4, we know is rad2/2. Rad2/2, and the inverse of that is just pi/4. Again, notice that pi/4 was already in our domain. So we can just go straight to pi/4, knowing that those inverses undo each other. So B can be a little bit tricky because we have cosine of 4pi/3. If we were to graph 4pi/3, it would be down here in quadrant 3. Reference angle of pi/3, 4pi/3, that would give us a -1/2 x value. But remember, we get a cosine inverse of a -1/2. That's fine. But now we have to take the cosine inverse. And remember, the cosine is restricted between 0 and pi. So we go, okay, so where does cosine equal negative 1/2 between just 0 and pi, we can use that same reference angle. And so instead of 4 pi over 3, we know we'd be up here at 2 pi over 3. And again, you can check it with your calculator, but we want to try to do it without. Now see, now we have two different trig functions. We have to figure out where sine of pi over 2 is. Again, if we're doing the unit circle, we can draw it over here. You have pi over 2, 3 pi over 2. This is technically 2 pi or 4 pi over 2. So we'd be back up here at 5 pi over 2. So we're up at the very top. So the sine value up there is 1. So that gives us the tangent inverse of 1. And remember, tangent, the inverse, is restricted between negative pi over 2 and pi over 2, not included. So the only time the x and y values are the same are at those 45-degree angles. So we would be at pi over 4. So again, it's kind of a little puzzle. You work on the inside first, and then wherever your inverse is, be sure that answer for that inverse is within your restrictions. Example 3, we want to find the exact value of cosine of sine inverse of 2/3 without a calculator. Okay, so now we're going to have a little bit of work to do. So we can use either our Pythagorean theorem or we can use right triangle trig. They're both the same. So remember, for sine of an angle, it equals y over r. So we can say we have a y value of 2 and an r value of 3. So if we're doing right triangle trig, we can say that the y value is 2, the r value is 3, and we can use Pythagorean theorem to find our x. So we know x squared plus 2 squared should equal 3 squared, plus 4 equals 9. So that gives us an x squared equals 5. So our x would be the square root of 5. So that means that the cosine value of that angle, which is x over r, would give us a rad 5 over 3. Or we can do the granddaddy Pythagorean theorem, where we have cosine squared theta plus sine squared theta equals 1. So we know that the sine inverse of 2/3, so of the angle, it would be 2/3. So 2/3 squared equals 1. Plus 4/9 equals 1. So cosine squared theta equals 1 minus 4/9, which would give us 5/9. When you take the square root of both sides, square root of 5 is just square root of 5. Square root of 9 is 3. So you get the same value. They're both based on the Pythagorean theorem. So we don't know what angle this is. All we know is we want the cosine of whatever that angle is, and we have found it twice, actually. Just two different ways. So cosine of theta is square root of 5 over 3. Now we want a trigonometric expression, tangent cosine inverse of x, and we want to write it as an algebraic expression in x between -1 and 1. Sorry, guys, I'm losing my voice. Well, remember, this cosine inverse is still representing some angle. And cosine of theta would be your adjacent over your hypotenuse if you're using right triangle trig. So we can write that as x over 1, okay, as that ratio. Tangent of theta is opposite over adjacent. Well, we know the adjacent is x. We just have to figure out what the opposite side is. So again, we can draw our right triangle with our theta. We know the adjacent side is x. We know the hypotenuse is 1. I'm going to label this other side a, because again, we want it in terms of x. So let's solve for a. We'll have x squared plus a squared equals 1 squared. So a squared equals 1 minus x squared. Then we take the square root of both sides and we get plus or minus the square root of 1 minus x squared. Remember, tangent could be positive or negative if the cosine inverse is in quadrant 1 or quadrant 2. So we can now fill that back in. If we're looking for the tangent of that angle, which is again opposite over adjacent. We know that opposite side now is square root of 1 minus x squared divided by x. So now we have written tangent of theta as an expression in terms of just x. All right, guys, last example in this section, we want to consider this right triangle below, and we want to find angle theta in both degrees and radians, okay? So notice the only sides that we have in reference to that theta is the opposite side and the hypotenuse. So which trig function uses the opposite and hypotenuse? That's the sine. So we know that the sine of theta in this instance would equal 6 over 10, or we can write it as 3/5. But we want the actual angle. So that's when we would take the inverse function, if we know the sides, and try to find theta. So again, why are we learning the inverse function? Is so we can have different unknowns. X could be an unknown, Y could be an unknown, the hypotenuse could be an unknown, now theta can be an unknown. So we would have to put these in our calculator and be sure that we find both the degrees and radians. All right, so first we want to check to see what mode that we're in. Let's go down here to mode. And look right there on mine, the fourth one down, we are in radians. So let's find the radians first. So we're going to go to second function sine to get the inverse. We're going to take this inverse sine of 3 divided by 5. And so we get theta in radians, 0.6435. And again, those are in radians. For us to do it again to find the degrees, we need to change the mode. So we're going to go back to mode. We're going to toggle down where it says radians. We're going to go over to degrees and hit enter. So now we're in degrees. Second function quit to get out of there, and we're going to repeat. Now to repeat it, we can put second function entry, and it just copies the previous problem, and hit enter, and now they're giving it to us in degrees. So theta equals approximately 36.87 degrees. All right, team, so we have both the degrees and radians, We have both the angles in radians and degrees. All right, if you have any questions, you know where to find me. Thanks, guys. Talk to you soon. Bye.